So we talked a little bit about this green and Ampt model. And the green and Ampt model, remember, we had the idea that this system was saturated behind a wetting front. Here we're looking at horizontal infiltration from this side going into the problem. And we found that the flow into the problem was equal to the saturated conductivity times the wetting front potential divided by the distance here. We also saw that the flow was equal to 1/3 of the velocity of this wetting front moving, right? And then what is the velocity? The velocity is just 1/3, and by the way, we could just say this was the porosity. Of our system. It's 1/3 times the change in distance per unit time. Okay? Aha! Now, I've got a Q equals this, I've got a Q equals this. Why don't I bring those together? And let's see what that gives us. So what we have then, and I'm going to go ahead and put in porosity there. I'm going to say that the porosity times dl dt is equal to Ks times HWF over L. Well, this is a terrible thing. We have L's here, we have L's there, we have T's here, nothing there. Let's separate variables. So we're going to multiply both sides by L, and that'll cancel this L. I'll leave it as L there. And I'm going to multiply both sides by dt. And that'll cancel my dt there, and it'll leave me a dt there. And so when I've done that little trick, what do we end up with? We get NL dl equals Ks H wetting front dt. That's a pretty simple equation. L's there, T's there, very handy. And so what I'm going to do is take the integral of both sides. And I'm going to integrate from 0 to L, and I'm going to integrate from t equals 0 to whatever time it took to get to L. Well, the integral of dt is just t, so that gives us Ks H wetting front t, and this will be evaluated between 0 and t, so that gives us naturally just the t. On this side, we have the n is a constant, it comes out. The integral of L is just L squared over 2. And again, we'll evaluate it from 0 to L, so the 0 contributes nothing, and we end up with just L squared. Aha! Let's solve for L. So what we then end up with is we'll multiply both sides by 2 and divide by n, and we'll take the square root. So we're going to say L is equal to the square root of, and now it's going to be Ks over n. There'll be a 2 there. There'll be a wetting front potential. And there'll be a T. And this is super important. What we see here is that the growth of the length of wetting goes with the square root of the time. So in other words, if we tried to go out to another distance L out here, how much longer would it take? If our first L took 1 unit of time, 1 minute, 1 hour, whatever, our next would take the square of that, so it would be 4 units of time. So at t equals 1, we've gone 1 unit of L. At t equals 4, we went 2 units of L, because the distance goes with the square root of the time. So when L equals twice as big, it takes 4 times as long. It also shows the relationship between saturated conductivity and displacement is also square root. So if I double the saturated conductivity, it only increases the distance by 40%. And it shows the wetting front potential in the same way. So this one equation shows how basically horizontal infiltration goes with the square root of time. This was all using the Green and Ampt approximation, but it turns out this exact solution, the same relationship between time and space, works if you use a numerical model or if you solved exactly using the Richards equation, you get the exact same square root of time behavior. So there's a fundamental feature of infiltration that the length of infiltration goes up with the square root of the time it's been exposed to water.